Hello, everyone. My name is Kevin McGehee. I'm a principal engineer on the Amazon ElastiCache team. I work alongside Madeline and others here that have presented. And I'm here today to talk to you about another proxy story. So we've talked, a lot of the previous presenters have talked about RESP proxies. And I'm here to talk about how we in ElastiCache Serverless built a high-performance RESP proxy and some of the learnings that you could take back to building your own proxies. So first I want to talk about why a proxy, why it's important to ElastiCache Serverless, and then talk about how we built it, how we architected it, some of the implementation details, and then how we maintain quality of service of this multi-tenant proxy at scale, some of the learnings that we had from that. So first, let's talk through why a proxy. What is a proxy? Why does it make sense? Before we get there, let's talk about what ElastiCache Serverless is. So we talked a lot about, in the past presentations, about running Valky clusters that are composed of lots of nodes, hundreds of nodes, thousands of nodes in the extreme cases. That all takes management. You have to know when to scale out, when to do your resharding. What ElastiCache Serverless does is it allows you to do automatic scaling, so based off of the different dimensions that you would scale out by, compute, memory, or networking. It allows you to do pay per usage on computer and memory, and it provides high availability out of the box, so you have three copies of all of your data across 3 availability zones. And it also does automatic software upgrades, so you don't have to do management of upgrading minor or patch versions. But the part that I want to focus in on today is the single endpoint experience, which is also included in the out of the box in ElastiCache Serverless. So let's talk about why single endpoint is important and some of the challenges that that motivated us to actually solve this problem and caused us to introduce a proxy. So if we look at cluster mode enabled, which is what serverless supports, you have multiple different shards here. So you have your application is talking to, in this case, 3 different shards, and they can be either primaries or replicas. And in order to actually figure out who to talk to, the default cluster mode protocol goes directly from the client to the node that owns the data. So to figure out where all the nodes are, it has to do a discovery. And so it sends either a cluster slots or cluster nodes command based off of some initiation seed node. It gets back all of the different slots to IP mapping. And at that point, the client can then go ahead and connect to all of the nodes. And it should theoretically know, based off of the hash of the key name, where each of those keys lives. And so if it's trying to get a key foo, it can go directly to the primary or replica on shard 2, which owns that data. So that works pretty well, but it's tricky to get right, especially when there are failures. And we've noticed through operating large clusters at scale, a lot of our customers had challenges on the client side with changes that happen in the cluster. So let's say a node were to actually fail. Let's say primary 2, you were communicating with it, now it goes down. If you were to try, the next time that the application wants to get that key foo, it might not know that, so before that even happens, we'll do a failover. So the cluster will transition, the replica will take over the role, so that now you have write availability restored in your cluster. And as far as the cluster is concerned, everything's operating fine, it's just down 1 replica. But the client's has to get that information back and might not know that it's, the failover has occurred. And best case, you'll get a TCP reset, and the client will notice that the connection has failed, but that's not necessarily the case. And so in this scenario, let's say it hasn't occurred, and we'll try to reuse that same TCP connection. We'll issue the GET against the now deceased primary, and what will likely happen is that that request will time out. And so this is an application-dependent setting that you would configure when you're initiating the connection. It can be sometimes short, sometimes very long, where the client's just waiting for a response that will never come. At that point, it still doesn't know how to get the item. It just knows that the connection's timed out, and so it has to go through that whole discovery process again to see if the failover has occurred, and where to go to next. So it has to go to slots, get back the IP mapping. At that point, it knows a failover has occurred where the primary has failed over to the replica, and it can now issue get foo on the new primary. So that all takes some amount of time, depending on the settings, and can result in a poor experience, because what should have been a sub-millisecond cache lookup can be even in the order of seconds, depending on what these timeout settings are configured for. Before we talked about resharding in one of the past presentations and how it's better now without the asked responses on every key, but there's still challenges in resharding, even if you're doing movement of data at a slot level. So let's say you're introducing, you have a 2-shard cluster here with primaries and replicas, and you're trying to introduce a third shard. So in this case, you want to be able to move a third of the data from primary 1 and 2 onto primary 3 to be able to even out the data distribution. And so Valky can do that with the new advancements using the atomic slot migration. But what happens after each slot is moved is that the client still needs to get updated. And we talked a little bit about how you'll get back these moved errors whenever that occurs. And at that point, the client then has to rediscover topology, know that, okay, there's a new shard here, I have to connect to that, and then issue all of the requests for that slot to primary 3. And so that usually doesn't require a timeout because that's an immediate response back, but it still adds another round trip from the client perspective and adds new latency for every single slot that gets moved. And so if you're moving thousands of slots, that could happen potentially thousands of times depending on the TPS of your application across every application node. And so this can be a pain point as well. Let's see. So we wanted to solve all of these different problems as well as others involved in the client experience by introducing what we call the single-endpoint emulation. And so this was the idea with this. What serverless provides is basically an abstraction that just shows a single virtual shard. So it shows one primary and one replica. And this is enabled by the proxy, no matter how many different nodes are behind the scenes in the backing Valky cluster here. And so this allows you to see a fixed topology from the client perspective. No matter what you call, you'll get back the same set of shards, even if the cluster resharding significantly behind the scenes. It means that there are fewer different disconnects and timeouts that can occur while you're using it, and no moved responses to the client. So you can basically use a much less complex client. It moves a lot of the complexity of handling failures from the client side to this middleware proxy. So let's look at what the requirements were when we were trying to build the proxy. First, we wanted it to be cluster mode enabled compatibility so that existing clients could use this without any sort of protocol change when they were to drop in this serverless. We wanted this to be low latency. We'll talk about this a little bit later, but we wanted minimal additional hops involved in introducing a proxy because a proxy necessarily involves additional hops, whether they be on or off box. We wanted this system to be, in general, support high throughput. So we designed this proxy to be scalable and stateless. And we wanted it to be efficient and cost effective, which drove us to build it as a multi-tenant system instead of a single tenant system. So let's go over some basic networking design. So in a normal cluster mode installation, you have most customers run their applications across multiple availability zones, or from AWS we call them availability zones, but similar thing data centers would apply elsewhere in other clouds. And so you'd have multiple applications across AZs here, and you have your nodes spread out across the different AZs. So in this case, the different colors indicate the different shards, and you could have primaries and replicas distributed across your shards, so you have local access for each of the shards that you need to. In terms of just general timing constraints, going within an AZ is maybe on the order of 100 microseconds from a round trip time, whereas going across availability zones can be on the order of 1 millisecond of round trip time. So it can be about a 10x difference, so which is why you'd prefer to keep the traffic within the availability zone as possible, not only for latency reasons, but also because there's often a cost associated with going across availability zones as well. So we tried to design a network topology to minimize the number of cross-AZ hops that needs to occur in the steady state. So same diagram before, but here we have customer VPC and then the service VPC, which is what ElastiCache provides, but you could do this within the same VPC. So we introduce a VPC endpoint for each of the, within each of the VPCs, and so that is the connectivity into the service. Each of these VPCs is fronted by a DNS name. So you have a single DNS name that you can use that has then AZ local DNS. So no matter which AZ you query it from, you get your local VPC endpoint, which means you stay within the availability zone to get to basically a set of network load balancers that are backed by that VPC endpoint. That allows us to do the RESP-based protocol load balancing. Those load balancers are backed by this stateless fleet of proxies within an auto-scaling group, so they'll scale in and out based off of traffic that comes from the front-end clients. And so as each time a connection is established from a Valky client here, it'll go through the NLB. It'll choose a proxy machine based off of which one is least loaded at that initiation time. And then the proxy can discover the backing Valky cluster and initiate a connection based off of which client is connecting and which data is being requested. So that proxy then can fan out to multiple nodes. In this case, it can go across an availability zone. So if you want to look at how it actually looks if you were to connect to a serverless endpoint here using the Valky CLI, you connect just using a single DNS name, and that will then resolve to one of those different VPC endpoints on port 6379, which is the default port for Valky. And if you run this cluster slots command to see what it exposes, you can see that there's one single shard, and it owns the entire slot range from 0 to 16383. And it has two different nodes, one of which is running on 6379, and one of which is running on 6380, but they have the same DNS name. So your client only needs to know that one single DNS name. So why are there two different ports here? Normally the first one here is the primary and the second one's the replica. And so how does that work? So in our proxy, we listen on two different ports from a client perspective. So 6379 is the primary port. So whenever a connection comes in, we will direct it to the primary when you're making a request for that key. So that gives you strongly consistent reads and writes. And 6380 is for AZ optimized or latency optimized requests. And so similar to how you would connect to a replica in Valky cluster mode, it will connect to a replica or a primary. It prefers the node that's in the same availability zone. So it tries to minimize the number of cross-AZ hops. So in best case, there's 0 cross-AZ hops when you connect to that 6380 port as opposed to the 6379. We talked a bit about multiplexing in previous talks too, so I'll go through this a little bit faster. But the naive way of implementing a proxy here would be to, every time a client connection comes in, to create a new connection to the primary. So okay, client 1, we create a new one for client 1. Client 2 comes in. So basically every single inbound connection is associated with a single outbound connection to a primary. But there's a lot of reasons why this works inefficiently. It works inefficiently in Valky just because the more connections you have, the more overhead there is in doing small I/O and small requests for each of those different connections. What's more efficient in Valky is to do larger I/O requests, which is why things like pipelining and batching work a lot better. We talked about some of the improvements in like I/O threading that help make that a little bit less, a little bit more efficient by offloading the I/O to separate threads. But it still would reduce CPU usage on the backing Valky cluster overall by trying to consolidate those requests. And luckily with this architecture, we have something that consolidates all of the requests. And so we can coalesce requests across clients into a single TCP stream when they're going to the same node, which can make it more efficient on the back end. So what that looks like in ElastiCache Serverless is we built a multiplexing protocol that's sort of strapped onto the Valky node and allows us to initiate a single TCP connection. So let's say a connection comes into 6379. We'll just do one TCP connection here, and then for every client that comes in, we can create a virtual client connection then and interleave them on the same TCP stream. And we've resolved things here with head of line blocking issues. We're able to interleave different clients as they make their requests, but still take some advantages from the efficiencies that sharing a TCP connection provides. So let's talk through some of the trade-offs of a proxy before we jump into some of the implementation details. So proxy isn't a free lunch. It's not a solution to every single problem. There's certainly some benefits. So the reasons that we pursued it for a serverless is primarily for the simplified client experience, because we wanted to make it easy for any client that is running across the open source ecosystem to connect without having to deal with all those failures we talked about earlier. It reduces some specific problems. So like in cases where you have a large number of clusters, now you have lower IP address utilization. You don't have to have single IPs for every single node that you're connecting to directly. And you don't have to have this large connection fan out from your application node. You don't need to connect to hundreds or thousands of nodes in your cluster. You just connect to initiate one connection. And the multiplexing allows you to reduce the CPU load on your back-end cluster. There are, however, a bunch of different challenges in introducing a proxy into your architecture. One is the number of network hops. So obviously, the architecture I talked before has additional network hops. We have this middle layer of proxies. We have this load balancer. And so that adds latency. And we've measured it in ElastiCache Serverless on the order of about 600 microseconds end to end after our optimization. So it's not free from a latency perspective. It adds additional costs because you now have to maintain this additional proxy fleet, and not only from the monetary cost, but also from an operational complexity standpoint, because you have to now operate this additional layer. And then there's some complexities just from the Valky command set. So we talked before about how it's easy to do just mapping set and get to an individual node, but things that are a little bit more challenging. So scan is an example of a command that is normally targeted at a shard to kind of comb over the key space. We solved that problem by doing a kind of a cluster-wide scan and having a cursor that goes across all of the shards. Similarly, for pub/sub or watch or Lua or any of these sort of one-off commands that don't map neatly to a single shard, you have to do special code for within the proxy to be able to handle them. And that's often why a lot of Valky proxies aren't going to be fully featured with the entire command set, and also why, for example, ElastiCache Serverless doesn't support 100% of the command set of open source Valky as well. And lastly, one of the challenges that we're trying to address now is just reduced customer visibility. So if you're operating this yourself, you have a little bit more control over the middleware, and you can see the commands that are coming and going. But from the outside perspective, you don't have easy ways to get things to like slow log or monitor that normally run on a per node basis. So if you're able to still kind of connect through to the nodes, you can do that, but from ElastiCache Serverless at least, those aren't visible. And so this is some of the observability that we're working on addressing to give customers still some more visibility into the underlying architecture while still keeping that abstraction in place. So let's talk a little bit about how we built the proxy. We talked through the architecture. So how did we build it concretely? So we decided to build this in Rust for its efficiency and memory safety. And we used the Tokyo library for its highly efficient asynchronous network I/O. But instead of using Tokyo's default sort of work stealing scheduler, where different client tasks would be queued across threads and just kind of go whichever thread had space, we overrode that and do our own assignment so that client tasks are pinned to a specific thread. And this we do for both avoiding synchronization issues, because now a single client task doesn't need to synchronize across threads, as well as to have better cache locality. A couple different performance tips that we learned along the way is one that might be obvious, but it's a little bit harder to do in practice, is to avoid expensive work in the hot path. So obviously the proxy, any processing you do while the proxy is running will add latency to your end command, and you want to make that work as small as possible. So things like deallocating a response buffer after sending it, something that's sort of obvious, isn't critical to the command. You've already sort of sent the response back, and we want to now deallocate it. So we want to be able to, in these cases, we post it to a dedicated background thread and have that background thread do that asynchronous processing so it doesn't interrupt any of the client processing threads. If we're not able to do that, then we yield frequently at least, to be able to allow other clients to run on that thread without blocking them. We also try to avoid any heap allocations where possible. Oops. So whenever it's not necessary, we would post it and reuse buffers as much as possible. One other sort of Rust-specific performance trick that we use is to avoid dynamic dispatch for traits on the hot path. So the default way of doing this would be to use a dynamic trait here, which introduces this vtable pointer lookup. And that it might seem small. It's only a couple of different CPU cycles, but it can add up over time, especially if it's being used frequently. And so for a lot of the traits that we've introduced for like connection types, where we might have a mock connection type, a TLS, a non-TLS, we use static dispatch, which kind of duplicates the code and can create a larger binary. And so our binary is quite large if we have, for the traits that we have lots of types for, but it reduces some of that runtime execution time. So if we look at a graph, this is of Valkey 8.0 of starting up from 0 TPS, scaling up to 5 million TPS over the course of about, I think this is 13 minutes of time frame, yeah. So as load ramps up from the client, we can see that the cluster is scaling out seamlessly behind the scenes, but this P50 read latency, which is the NAZ read latency I talked about before, remains sub-millisecond. It's a bit hard to see on this graph, but it's slightly below the 1,000 microsecond latency. And then this P50 write latency, which can cross an AZ because it still needs to go to the primary of the shard, is slightly above 1 millisecond mark. And then the P99 get and set latency is a bit higher, and those are things that we're still working on trying to bring down to be more consistent. So last I wanted to talk through managing quality of service, which was ensuring how we can maintain performance of this multi-tenant system at scale. So it might not come as a surprise, but everything has limits, even those that don't document limits. Every machine does have natural limits, and so you can scale your way out of some problems, but you can't scale your way out of every single problem. So you need to think about how, as you scale, you'll be able to handle client traffic and what problems you can and can't scale out. So let's go through a concrete example. I showed you this graph before of how the network architecture, and I kind of lied here a bit because I showed that there were 3 VPC endpoints and 3 network load balancers. But those network load balancers are backed by physical machines, and they have scalability limits as well. And so we wanted to avoid having any sort of single point of failure in this system, especially those that were used in multi-tenant systems. And so rather than having 3 VPC endpoints, 1 per AZ, we actually have 3 VPC endpoints by default in a single availability zone. So 9 total by default across the VPC, each backed by their own network load balancer, with the ability to sort of dynamically scale those up and down. And so that these network load balancers are going to be our shared multi-tenant systems, and so it allows us to better control scaling and heap management across the different tenants on the system. So one client or one application can't completely overwhelm them. We're able to shift traffic around and using DNS load balancing get customers onto different load balancers. Then if we narrow into just a single proxy, we talked about assignment. A single client would be assigned to a proxy. Those proxy machines, even though they're in an auto-scaling group, have limits themselves. So they have, each thread has a certain amount of CPU that it is allocated, that it can use, as well as the machine as a whole in terms of networking and in terms of memory. And so all of those are real limits that you have to be cognizant of. So we can make assignment choices when a client connects, but we don't necessarily know what that client's going to do. It's just connecting for the first time. It might send a little bit of traffic. It might send a lot of traffic. So we can certainly have the condition where we have a bunch of clients connected, but all of a sudden they ramp up their traffic in tandem, and now we are CPU constrained on that thread. And so we have to do something about it, or else all of the clients may suffer on that. So what we've done to handle the same thing is true for both networking and memory, but across all of the threads here. So the baseline control that we have within the proxy is basically twofold. One is throttling, and we can do either implicit throttling, which we do throughout by limiting the task granularity and adding yield points. So that means if there's just one poorly behaved client that's trying to send a lot of traffic, that it won't negatively impact all of the other clients. It just might get more rate limited. So that's sort of implicit within the language. And then there's explicit throttling that we use. So we can refuse to read more data from a client if it's sending a bunch of data and sort of not consuming any, and that can bound its CPU and memory. But throttling can only help so much, and we don't want to be throttling indefinitely. So the other fallback control here is client eviction and scaling. So this is the way when you can scale your way out of the problem by adding more hardware to the problem. And so by moving clients around, we're able to get them to reconnect, send them to different proxies that might have more resources. But it's more expensive because it requires a client disconnect, which we want to try to avoid since it can be impactful to clients even to disconnect them. But it allows us to more evenly distribute the load. So the other thing that we did throughout this is to add limits where possible. So we talked about the hardware has explicit limits. We often don't like to think about limits when we're offering services, but where it's able to add better guarantees, we try to do so. So we added, in a couple places, external limits that are hard that will generate an error when a user comes in. So an example of this is a key name and a Lua script. So we in ElastiCache Serverless, we limit key names to 4 kilobytes and Lua scripts to 4 megabytes, which based off of our ElastiCache user data encompass the vast majority of customers. And those are just ones that allow us to limit the memory used within the proxy as we're doing the parsing. And then there's also a number of different internal limits as we were building this that are either hard or soft and can cause those throttling or eviction controls that I talked about further to improve safety. So example of this would be something like new connection rate, where if a new clients are single applications are connecting more often than not, we'll end up throttling them. And pipeline depth being another one. If you have a bunch of unacknowledged commands and continue sending more, then we might rate limit you. Thanks so much.